First, we're going to have a little homework. We haven't had any for a while. So let's see what we have here. I think we're at session number 25. Okay, so let's look at homework. And this will be due next Monday, a week from today. Okay. So firstly, we have the required problems. And these are Chapter 12, exercise number 1. Number 1 is a bull spread. 4A is a result we've already used on the option premiums for different values of strike price. And 8A. Okay, plus describe. This is an easy problem. The Dow. So this is the Dow Jones Industrial Average. When you see, it'll be the Dow of 30 stocks. The S&P 500. And if you see, the last I looked, the market was up again today. So all these indices are reaching new highs. The NASDAQ. And we have the NASDAQ, the composite. Plus you have the NASDAQ 100. Now when you see on MSNBC or the New York Times or the Wall Street Journal, you usually are seeing just the NASDAQ composite, not the NASDAQ 100. And then the Russell 2000. All these indices have probably today will reach new highs. They have reached new highs this past week. If they stay up today, they'll reach new highs. Now, the extra credit problems will be as following. Once again, Rubenberger exercises are, for the most part, pretty difficult. So why don't we do Chapter 12 exercises. Number 2 and 4B. We did 4A as a required homework. Now, let's see where we were before. Last time we were looking at the last time we were looking at the binomial lattice. and that's a binomial lattice option pricing. Model. We could call it a formula or anything. Now, what we pointed out that the binomial lattice, the lattice grows linearly whereas a tree, we had a binomial tree, grows exponentially. So a lattice is a lot easier to compute. In the lattice, there are a number of ways to reach a common node. In the tree, there's one and only one way to reach each node. Now, how do we use it for call option pricing? Okay. Now first let's consider the single period model. A single period model. And this is in section 12.5, page 327 of our text. Okay, now to derive the one period or single period call option pricing formula, it's called an equation. We, following Leuenberger, our textbook, use the concept of a replicating portfolio. Remember, we've used this concept before in the put-call parity equation. And this is the idea of a replicating portfolio is used throughout finance and financial engineering. So let's see what we mean by this replicating portfolio. This is pretty easy. And it's kind of cute. Okay. Okay, our replicating portfolio consists of holding X dollars worth of the asset. Let me make sure this is an X. In other words, typically the asset we consider as a stock. And at the same time, investing B dollars in a risk-free asset. As depicted in figure 12.5, page 328. So we hold X dollars worth of the asset here. Here's our stock. And we know that our stock in a binomial lattice can go up, what, to US, or it can go down to DS. Now, we also have, if we talk about a risk-free asset, we know that $1 can go up to, after one period, to R dollars. Okay, and let's look at our call option. Our call option is the following. Our call option can do two things. It can go up to the maximum of US minus K. This is the value of the call option. Or it can go down to max of DS minus K. K is our strike price, of course, and 0 here. And this is CU, and this is CD. Okay, so that's the call option if it goes up, and the call option if it goes down. Let's put this here so we don't miss it. Okay. Now, we're almost ready to give the price here, the pricing formula. Let's look at that. Let's see if we right ahead. So we set UX plus RB equal to CU, and this is equation. The book derives this. I may go over the derivation next time, but it's really not necessary. Equation 12.5a, page 328. And we set dx, this is our down, plus RB equals CD. That's equation 12.5b. Again, the same page. Okay. Now using these, equations, we can derive the value or let's just call it the value C of a 1 period call option and that is the following. Let's call this C. We'll say that that value equals 1 over R times Q CU plus, let's cross these capitals, plus 1 minus Q CD. Okay, so we have C up and C down. And this is equation 12.8. Page 329. So I haven't, let me get a different color pen. I haven't specifically derived that, but the book derives that. I may derive it next time, or I may just skip it. It's mainly a bunch of algebraic gymnastics to derive this formula. Okay. So let's do that. Okay, good. Okay, and in this, let's look at Q. We have a Q here and a 1 minus Q here. So a Q looks a lot like a probability, and in fact, it's going to be called a risk-neutral probability. Q equals a risk-neutral probability. And we can define Q equals R minus D over U minus D. C. And Q is greater than or equal to 0 and less than or equal to 1, since we had assumed that U was greater than R was greater than D. Okay, remember we said that was, we assumed that for no arbitrage. And this was I'll try to write a little bigger than that. That's pretty small. Okay. Okay. Now, what do we want to do? Maybe we can put that here. Okay, here. The pricing formula can be viewed as setting C, the value of the call option, equal to the discounted and it's discounted because of the 1 over R term. Expected value of the call option. And the expected value is because of the Q's and the Q's we viewed as the risk-neutral probabilities. Here. So we have Q and 1 minus Q. Okay. Got a little ahead of ourselves. Okay, now here, let's do a numerical example. Let's do a numerical example. Okay. And we'll do a pretty simple numerical example. We'll say that suppose, and we're going to use some data we used before. Suppose the stock price now equals $50. Of course, that's $50 a share. Okay. And in one period, it can go up so this is a volatile stock to $75 equals SU okay, or go down to $25. So it can drop by a half, and it can go up a half equals SD, and therefore we have that U equals 1.5 and D equals 0.5. Okay. Okay, let's also assume the following. Assume that the one period this is a very unrealistic interest rate equals 25%. And now we know that yearly interest rates are very, very low now. In fact, the federal funds target rate is between 0 and 0.25%. Or, this is R, if we express it without a percentage, is 0.25. So that capital R, our return, equals 1 plus R equals 1.25. Okay. Therefore, we satisfy our no arbitrage assumption. Since we have what? Since U equals 1.5, which is greater than R, equals 1.25, which is strictly greater than D, equals 0.5. So we satisfy our no arbitrage condition, this example. Now, of course, these are highly unrealistic, this interest rate of 0.25, and also we have a very volatile stock. Even given that a period is a year, you would hardly expect it to go up by half or go down a half. Now, let's see what we can get here. Let's look at what is the call option. Okay. Let's also assume that the strike price equals K equals $50. Okay? So we're at the money call option here. Therefore, with these data, we have the following. Therefore, CU equals what? Equals the maximum of 75 minus 50, or 0, equals $25. Remember, this is US up, again, that's 1.5 times 50. And this is our K, of course, our strike price. Okay. And we have CD equals the max of 25 minus 50. Now this 25 is DS. This is again our K, or 0, equals $0. Okay. And what else do we have? Our risk neutral probability is what? is Q equals R minus D over U minus D, well, lowercase u minus d, equals what? Equals 1.25 minus d is 0.5 over what? Over 1.5 minus 0.5 equals what? Equals, on the top we have 0.75, and on the bottom we just have 1. So it equals 0.75. That's a pretty high probability. And by the call option pricing formula, okay, let's plug all these things into our call option pricing formula, see what we get. One period call option pricing formula. Let's call it equation 12.8. We have what? Let's plug these values into our call option pricing formula, see what we get. We get the value of that call option equals 1 over R, this is our formula, remember, times Q times CU plus 1 minus Q. This gives us our discounting. The Q's give us our expected value, CD. This is our equation. Now, if we plug our numbers into here, what do we get? We get that this equals 1 over 125. Remember, capital R equals 1 plus little r, times what? Times 0.75 times 25, that was CU, plus 0.25, 1 minus Q, times 0. So this goes to 0. And we get the following. We get that this is equal to 18.75 over 1.25, okay, equals $15 if you work this out. So this call option is worth $15. Now, note also that our risk-neutral probability Q satisfies the following equation for the stock price. Yes. Okay. And if we look at this, if you think about it, this is not surprising. Let's look at the equation. This equation is the following. is that the stock price equals 1 over R. Okay, again, we discount. Now we say Q, US going up. So we're looking at one period what happens, and we discount it back, plus 1 minus Q times DS, which makes perfect sense because we can go from S to US and down to DS in the next period. So if you bring that back one period, you get this equation here. And this is page 329. Maybe it doesn't have a number. Okay. So let's look at that. Let's plug in our data. The examples data, we get what? We get that S equals 1 over 1.25. R is 1.25. We know that Q is 0.75. CU, remember CU, we started at 50, and we said we could go up to 75. 1 minus Q is what? Is 0.25. 0.25. We could put a 0 in front of these guys if you want. Times what? Times, remember we could go from 50 to a half of 50 down to 25. And if you calculate this out, you get 1 over 1.25 times what? Times 56.25 plus 6.25. Okay. So what is that? That is 62.5. And so in fact, that equals $50, which does equal our stock price, our initial stock price. So it checks out. And it's not surprising that it checks out here. Okay, let's see what else we have here. We want to do. Okay, let's see what else we want to do now. Let me check what I want to do next. Let's see what we got here. Okay, we got that was equal to $15. Oh, okay, good. Let's do the following. I think this is something that's not in the book, but is interesting. Good. Let's use another replicating portfolio. let's use another way, say, method of using a replicating portfolio to calculate C, which is the value, that's pretty bad, calculate C, is as follows. Okay. Let's look at time 0. After one period. So we're going to look at these two things. Let's see what we get here. So at time 0, we can write two calls. So to do that, the price of that we get 2C, right? Because we get that premium. That value is really the call option price or premium. Okay. So if we write two calls, the holder has to give us 2C. After one period, if S1 equals $25, or S1 can equal $75. It can go down or up here. So if it goes, let's do this. Let's cross this off and let's put this as 2C. So we're at the right level. If it goes up to $25, if it goes down to $25, then we know it's worth 0. If it goes up to $75, then we have to pay out 50 here. Okay. Now, if we buy one share of stock, so our asset is now going to be stock. It's going to cost us $50 here. And it either goes down to $25 if it goes down, or it goes up to $75. Okay. After one period, it's worth either $25 or $75, depending on if it goes up or down. Okay? Now, if we borrow $20, what can happen? The reason we're borrowing $20 is that it grows to $25 after one period. Okay, so if we borrow $25, look at that, this is plus $20 here. After one period, we have to pay back $25 And here we have to pay back $25, no matter if the stock goes up or it goes down here. So let's look at these. In both of these cases, if you go through it, what do you have? Here you have 75 minus 50 is 25, minus 25 is 0. Here you have minus 25 plus 25, you have 0. Okay, let's see what we have here. Let's see what our sum is. Equals what? Equals, we have a 2c minus 50 plus 20. So what does that equal? That equals 2c minus 30. And so if you set this equal to 0, then what do you get? You get c equals $15. Exactly what we got before. So this is another way to replicate that here. Okay, let's see what else we want to do today. Okay, now, the nice thing about this one-period binomial lattice is that it can be easily extended to n periods. Or one period binomial lattice can easily be extended to n periods greater than 1 periods. Okay. First, let's consider a 2-period binomial lattice. Okay. As in figure 12.6, page 330. Okay. Now let's look at this guy, this 2-period binomial lattice. We start off with C here. Then we go up to CU. See, C is the value of the 1 period, CU. Then we go to CD. And then we can go up again to CUU, or CU squared. Or what can we do? We can go up and down to CUD. Again, we can get there from this way, or we could go down to CDD. Okay. This is after 1 period. This is after 2 periods here. Okay. Now, we can use our pricing formula again. Then we can obtain Cu from CUU and CUD. Okay, so we want to look at the CU. We have up again and up down using our one period call option pricing formula. Equation 12.8. And likewise, calculate CD from CUD, and here's our CD, so we can go up to CUD if we go up, and CDD. Okay. Now, in the binomial lattice, we work backwards to calculate C. In our binomial lattice, we work backwards from the end to calculate C. Okay. So this is important, that the idea is that we're working backwards here to calculate our price here. Now, let's see. Let's stop here because we're going to get to some tricky stuff on how. Next thing we're going to do is how to pick U and D. These are critical about how much the stock goes up, the multiples, or how much it goes down. This is a little tricky. We'll go over this the next time. I think this is a good place to stop, even though we're a little bit early. I think about 5 minutes early. So pretty soon we're going to be we'll have all the tests in, and we'll be able to get the grades in for you guys. Okay. Thank you very much. We'll see you tomorrow. Keep reading that chapter 12. And also you have a little bit of homework to do. Thank you.